Hello, ladies and gentlemen. Welcome back. This is Mr. Dang, providing you notes for periodic trends. Hope you guys are ready with notebook paper. Title it Periodic Trends. So, today you will identify, define, and explain the periodic trends of atomic radii, ionic radii, electronegativity, and ionization energy. You will know what these are, you will know the trends, and you will know the reasoning behind it. And you will do a worksheet after these notes to practice and understand these a little better. So anytime you have questions or any concerns, you can always come to me in 503 and get some help. So here we go. Periodic trends. If you did the graphing paper earlier, you should know kind of an idea of what a periodic trend is. It's a repeated pattern on the periodic table that displays physical and chemical characteristics over and over again down each period. Okay, down each group. I mean, each period will have its own set of properties repeating. And the period, well, we need to know what a period is. A period are the rows. There are 7 rows on this periodic table. There's 1, 2, 3, 4, 5, 6, 7. So know that there are 7 periods, and how many columns? How many families? Families or groups, there are 18 of them. Okay, nice 18. And so here, period 1, 2, 3, 4, 3 to 12 is here. And then 13 to 18 here. 13, 14, 15, 16, 17, and 18. And when we talk about these trends, we're only focusing on period 1, 2, 13 through 18. These are what we call our representative elements. Transition metals are in the middle here. We're not going to talk about that as far as periodic trends because they don't follow these rules very well, and so it just causes more confusion. So 1, 2, 13 to 18. And so when we talk about periodic trends and we talk about the atom, what is precious to the atom versus what is precious to you? So certain things that you it's precious to you, you want to hold on to it, right? Like your phone. Just imagine you walk into the hall and somebody wants to take your phone. Oh no, you're not letting that one go, right? So what is precious to the atom? What's precious to the atom are its electrons. And just a quick review here. And before we review, see what's on the next slide. Oh, that's pretty precious. Yep, precious moments is. And so, okay, let's talk about precious here. So precious, an atom has the nucleus inside, right? Then around it, it has rings of electrons. So we can have electrons floating on the outside. And the inside, these things, the protons want to pull these electrons inward because protons are positive. Oops, that's ugly. Protons is positive and electrons are negative. So positive, negative, they attract each other. Okay, the protons, the nucleus wants to keep all the electrons pulled toward it. Okay, and so that affects the radius, electronegativity, and ionization energy, and you will see exactly why and how. Right? The first trend we're talking about is atomic radius, the size of the atom. The definition is the distance between 2 nuclei of the identical atom. It has to be identical atoms, just like 2 hydrogens. A hydrogen and a hydrogen, they are bonded together like that. They're supposed to be the same size, but it's not happening here. Hold on, I am struggling. So then here is the trend here. So then you measure the distance between both of them, and only half of it, which is this part right here, is the radius. Half the distance between 2 nuclei is the distance of is the radius, right? And so atomic radius, the size of the atom, it decreases. You can tell here, going left to right, just like our graphs earlier showed. Okay, going left to right. Notice it's a large atom, smaller, 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 even smaller as we go from left to right. But going downwards, going down, top to bottom, top to bottom, top to bottom, it is getting bigger, bigger, and bigger, and bigger. Atom gets bigger as we go down. And the reason is why. Okay, why, it says here. It says the electrons are being added to the same level, but the number of protons in the nucleus increases. Okay, and going down, why? The outermost electron is in a higher energy level, which is further from the nucleus, so the radius increases. And I will explain to you why here on this paper. So you need to understand how or why these things are so. Okay, so everything on row 2, lithium's on row 2, right? Period 2. It's going to have what we call 2 energy levels, or what we call 2 rings. Okay, it's going to have 2 rings. It's going to have 2 rings. And so when we talk about these rings, we need to consider 2 things: proton versus electrons. So lithium, it has 3 protons, 3 electrons. Beryllium has 4 protons and 4 electrons. Notice we still have the same number of rings. But the force that's pulling these electrons in, as I mentioned earlier, is the nucleus. So the nucleus is pulling these electrons in closer. Okay, so the nucleus, oops, that's ugly. Let me make this smaller here. The nucleus pulls these electrons inward, and the same number of shell, it says here, are being added, but the number of protons in the nucleus increases. The same energy level. 2 shells, and the nucleus gets stronger. Therefore, it's pulling it in closer. That's why it does get smaller from left to right. Okay, easy way to put it, I'll repeat that again. As we go from left to right, the number of energy levels stays the same. The shell stays the same. If we add more protons, it pulls the electrons in closer. That is why left to right, the atomic decrease. Top to bottom, it's an easier concept, because as we increase in the row, period 2 to going down to period 3 here, we add another shell. So basically 2 ring become 3 ring, 3 ring become 4 rings. Okay, I'm just gonna draw it out here. 4 rings become 5 rings. Guess what? The atom keeps getting bigger and bigger. The atom gets bigger and bigger as we go down because we add the number of rings. Okay, the outermost electron is higher in energy level. Adding the rings is adding energy level. So as we add more rings, of course it's going to be a bigger atom. So that's why. So largest atoms are on the lower left: cesium, rubidium, barium at the left hand bottom corner, and the smallest atoms are on the top right, like neon, fluorine, and helium on the top right. And the next thing, ionic radius. What is an ion? An ion is an atom that has gained or lose electrons. It has gained or lose electrons. Okay, we're not going to go into details of, well, we can. No, not yet. So the gain or lose electrons. If it gains an electron, it becomes negative. It is called a cation. Anion. I got that backward. An anion looks like an onion, but it's anion. And if it loses an electron, it becomes positive. It is a cation. Okay. And so an anion, if it gains an electron, guess what? So if you have 10 electrons, and it becomes 11 electrons, guess what? If you add more electrons, the electron cloud gets bigger. So let me erase this. That didn't make sense. So anion, you add electrons. So radius increase because electron cloud is bigger. Radius increase because the electron cloud gets bigger. Cation, if we take away electrons, right? We lose electrons here. Cation, we lose electrons. Then if we lose electrons, guess what? The proton's going to pull stronger. So less tug of war, sort of. There's 10 protons and 9 electrons. They're going to pull it closer. So then it gets smaller. So cation is smaller than the original element. Okay? So here, ionic radius is the distance from the nucleus to the outermost electron of an ion. Cations are always smaller because they have lost electrons. So then the nuclear pull, nuclear attraction is a lot stronger. The electrostatic attraction, nuclear force. Okay. Anions, the negative, these are negative ions here, are always larger because they gained electrons, expanding the electron cloud. They gain electrons, expanding the electron cloud. Here's a visual for you. Lithium, for example, here it says the ions are colored red and blue, and the parent atom is brown. So, cation. All this left on the left is cations. They're all positive. The brown is the original. Once it loses the electron, it gets smaller. It becomes that red. Losing electron gets smaller. Losing electrons, smaller. Losing electrons, smaller. Repeat after me. Losing electrons, smaller. Losing electrons, smaller. Yeah, you sound weird. You're just talking to yourself. Okay. And then to the right, here are your anions. They gain electrons. So guess what? They gain, so then the cloud gets bigger. Therefore, the regular nitrogen is going to be smaller, which is the brown regular nitrogen, versus the nitrogen that gained 3 electrons and minus 3 is bigger. When it gains electrons, get bigger. Gain electrons, gets bigger. Gain electrons, get bigger. Yeah, you get the point. Good. Moving on. Cation decreases size across the period. So saying the same thing over and over again here. Why? The number of positively charged protons increase. Valence electrons are still the same distance away from the nucleus. Cations, remember, they lose electrons, become smaller. Cation increase in size down a group. Down a group, still the same thing still applies. The same thing as the radius. Going down a group, there's still energy levels added. Okay, there's still energy levels added as we go down. Electronegativity. This is a fancy word here. Electronegativity. It's kind of weird. Negative and attracts, right? They want to be more negative, so they have to attract more electrons. So how attractive are these things? How greedy is this atom? Electronegativity is it's wanting more electrons. So guess what? Ew, that's so ugly. Ew, I don't even want to see that. So increases across a period. So it all of it is related to the size of the atom, and I'll explain why in a little bit. Increases across a period and increases up a group. Okay. As the size of the atom decreases, electronegativity increase. And so the most electronegative element is at the top of the right-hand table. So fluorine, oxygen, nitrogen are very attractive. The least are at the very bottom. Okay, because big elements, it has to depend on the size of the atom. So I'll talk about that in a little bit here. Let me get to let me get to a blank sheet here, and I will show you why. The reason being, as the atom gets smaller, here's an example. Mother takes 2 kids. This is mother, long hair. Yeah. Takes 2 kids to the mall. No, that's not a good example. Let's clear that. Let's start over. That's not a good example. That's for later. I'm jumping ahead of myself. So, electronegativity has to do with the size of the atom. Here you go. Here's the atom, right? Smaller atom. All has to do with distance. Remember, all this has to do with distance from nucleus. Because who's doing the pulling? From nucleus. Okay? All this has to do with the distance from the nucleus. So here's an electron that's floating around. Who's going to pull this stronger? Big atom here? Or a smaller one? Okay, think about that. So the smaller one is going to pull it. It's going to be more attractive because it's closer to the nucleus. So smaller atoms equal higher electronegativity. Higher electronegativity. So you'll write those down. Okay, smaller atom is equal to higher electronegativity because its attractive force is going to pull electrons in because it's closer to the nucleus. Bigger, so the opposite. Bigger atoms at the bottom here, francium, it doesn't pull electrons in as well. It's not as attractive because the atom is so big, the nucleus is so far from the electrons on the outside. The next, ionization energy. The energy required to remove an electron from an atom. Okay, so think about okay, let's continue. Electronegativity equals greediness. Oh, that's so ugly. Greediness is greediness for something shared. Ionization is the stinginess. How tightly these things are holding onto its its electron. So how much energy do you need to remove it? Okay, so ionization energy increases across a period. So going across, going left to right, ionization energy increase. Going top to bottom, it decreases. Why? Across it increases because valence electrons are more tightly bound and it takes more energy to remove electrons. It takes more energy to remove electrons. Ionization energy increases up a group, so basically decreases down a group. So think about it, we go down a group. What happens to the atom? It gets bigger going down a group, so then it's easier to steal its electrons. So back to that example I tried drawing earlier. So we go to the mall. Here's Mom holding Junior up here. Like Mom has to carry Junior. And then here's someone. Mom don't have spiky hair, so Mom's like that. So there's Junior here. There's another Junior here. There's a bunch of Juniors. Okay. So let's say if the energy, if let's say one of these poor kids, hypothetically speaking, no real true story, okay, just trying to make a connection here. So if one of these kids were to get snatched by someone, which one would require the least energy? It would be this guy right here, right? Because he's the furthest from Mom. Mom is not holding on to him as closely. The hardest, so the further it is, far means less energy to remove. Energy to remove. So when we have the big atoms, the ones on the outside here, less energy. Lower ionization energy. And versus a smaller atom, here's a smaller atom. Try to remove that electron. It's so much closer to the nucleus that it's really hard to remove. So smaller atoms will require higher ionization energy. Bigger atoms will require lower ionization energy to remove. So if you know the atomic radius trend, ionization and electronegativity will be so easy. Just know what they are and why it is so, okay? Has to do with the distance from the nucleus and the attraction of the nucleus to the electrons. And that concludes all the slides today. 17 minutes long of video. Is my first time making these videos, so I do make mistakes. And so if I do make any mistakes or if I did confuse you any way, let me know. And I'll come by, ask questions, and I'll help you out. Thank you. Goodbye.